Hello! In this video, we will continue our discussion on supervised learning. We will introduce the concept of generalization performance and discuss some techniques to measure how well our estimators would perform in real settings. Last time, we discussed the general concept of supervised learning. We have a box of tunable functions, some inputs x1 up to xt, and we want to predict y, which could be a classification or a regression task. To do so, we need input examples that consist of features xi and their respective labels y. This is called the training data. In supervised learning, we use this training data to train our tunable box. As we saw last time, the training process usually involves some sort of optimization. This means that from the collection of possible tunable functions, we select the function with parameters theta I that minimizes the training error. However, the important question is the following. If we deploy this model in a real-world scenario, how good will it be? Estimating the performance of our model for unseen data is a very fundamental question. In order to answer it, let's go back to our previous example of estimating final grades based on the average homework grade. Every point in the graph represents one example of the training data, and eventually we came up with this linear function in blue called y hat that minimizes the sum of squared errors, or RSS. If we take one training example xiyi, we said that the training error for this example is the discrepancy between yi and the corresponding y hat. We can of course compute the average error between our training data and y hat. This is commonly known as the training error or training performance. For example, if we have m data points in a regression problem, the training error looks like 1 over m times the summation of squared differences between yi's and y hats. In a classification problem, the approach is similar. We can count the number of incorrectly classified inputs and divide it by the total number of training examples, in this case m. However, this is not a good way to estimate the performance of our trained model on the data that we will see in the future. This is the concept of the generalization performance that we are going to discuss. We have used our training data to select a tunable function that minimizes the training error. However, we cannot reuse the training data to estimate the performance of our machine learning model on the unseen data. This performance is known as the generalization error, which is the error rate on future or unseen examples. In summary, since the training data was already used in selecting the function, we cannot trust the training error. It is usually too optimistic. That is, the training error is normally lower than the generalization error, which is the error that we observe when we test our model in a real-world scenario. Training performance is also known as in-sample performance. It is the error that we use to choose the parameters of our model. It helps us to find the best function that fits our training data. This performance is generally too optimistic, and we cannot use it to measure how well our model does outside of the training data. On the other hand, generalization performance, which is also called out-of-sample performance, measures how well our algorithm does when we test it with examples that the algorithm hasn't seen before. For example, in our classification task of dog versus cat, we use training images to tune our model. After training, you might say that your training accuracy is 95%. However, if someone uses your model with images different from your training data, they may see a much lower performance, say 80%. The key here is that the generalization performance is what we really care about. Now, how do we estimate the generalization performance? One simple idea is to divide your original training data into two subsets, a training set, which we use for training purposes, and a test set, also known as the holdout data, that is used to estimate the generalization error. For example, it is very common to use 80% of your data for training the model and then use the remaining 20%, which is the holdout data, to estimate the generalization performance. Since this holdout data was never used in the training phase, it gives you a more accurate estimate of the generalization performance. We can do a little better than that. We can perform what is called k-fold cross-validation. The idea is very simple. We have our initial training data D, and we divide it into a set of k blocks or folds. For this example, let's say we use k equals 5. Each time, we hold out one of the folds to be a validation fold, and the remaining folds are used as training folds. We train our model using the training folds and compute the error of the trained model on the validation fold. We repeat this step k times, in which each fold is a validation fold only once. Then the generalization performance can be estimated by taking the average obtained errors in the k iterations. Now that we have an estimate of the generalization performance, we can obtain the final model by retraining our model with the whole dataset. This way, we are using all the available data for training the final model. In general, typical choices of k are 5 or 10. The case where k is equal to d is known as leave one out cross-validation. In summary, in this video, we discussed that the training performance is usually too optimistic. We talked about the generalization performance, which is what we really care about in machine learning. This performance metric is also known as out-of-sample performance, and it is the error rate on the future or unseen data. We discussed the simple train-test partition, in which we divide the training data into train and test set, typically 80-20 or 70-30% respectively. We then talked about a better way to determine the generalization performance using k-fold cross-validation. Here, we divide the training data into k folds. Each time, we select one fold for validation, on which we compute the error, and the remaining k-1 folds for training. After training our model k times with the training folds, we can take the average error to obtain an estimate for out-of-sample performance. Finally, we retrain our model with the whole dataset to get the best tunable function.